Our next speaker is Lexing Ying. He received his PhD from the Cron Institute in 2004. Later, he was a professor at UT Austin before, very sadly, moving to Stanford University, where he is a professor of mathematics and also a member of the Institute for Computational and Mathematical Engineering. Among other distinctions, Lexing Ying received the James H. Wilkinson Prize in Numerical Analysis and Scientific Computing in 2013 for his outstanding contributions in many areas, including the rapid evaluation of oscillatory integral transforms, high frequency wave propagation, and the computation of electron structure in metallic systems. Today, he will be applying his expertise, talking about the application of deep learning in solving inverse problems. So with that, let's welcome Lexing Ying.
Yeah, okay, all right. So yeah, again, thanks Rachel for the very nice introduction, and also thanks to Jianfeng for organizing this conference. So, and I also like to thank everyone on the organization committee for inviting me for this talk. So today I'm gonna talk about some work that I have done with my previous postdocs, Yu Wei Fan and Yu Hao Kuo, trying to use deep learning to solve some inverse problems. And this talk is mostly going to be on the at the beginning of the talk. The first part of the talk will be more on mathematical side, and the later part of the talk will be more on the application side. Okay. All right. So let me get started. So the problem that we're trying to address is a very vast area. It's called the inverse problems, and we're trying to see that whether deep learning can make some contribution in the area of the inverse problems. So inverse problem is very important. And essentially, it's a big industry, multiple industries behind it. So the main idea of the inverse problem is to try to discover internal structures of a certain domain or certain object from boundary measurement. So at the top of the slide, I try to show several examples. So the first example is radar imaging, where you have a radar station sending electromagnetic wave, and it's trying to detect the shape of the incoming airplane, for example. The second image is a seismic imaging of the ocean. So where you have these geophones, which are sending out acoustic waves, and then you have these receivers on the cable is trying to receive this wave and trying to detect the underneath structure. The last picture is trying to show you also play an extremely important role in medical imaging. Okay. So mathematically, as I said, let's make it a little bit more precise. So mathematically, the inverse problem is trying to take the measurement data, which denoted by D throughout this talk, and trying to figure out what will be the internal parameter, which denoted by eta in the rest of the talk. So depending on the inverse problem that we're working on, often the problem itself can be fairly ill-conditioned, especially when you're working with low frequency wave or working with elliptic equations. And so therefore, typically we need a little bit of regularization during the inverse problem process. So this is the one main challenge. The second main challenge is related to high dimensionality. Because, we're trying to recover a field rather than just one parameter, because if you're trying to recover all the parameters inside a domain, eta itself is a function, it's a field. So therefore here, naturally, we're working with high-dimensional problems. And often this high-dimensional problem is nonlinear because the mapping between the data and also eta is nonlinear. Okay. Now, let me proceed. Okay, so the tool we're going to use is deep learning. And the deep learning has achieved many state-of-art performance on many computer science and artificial intelligence applications. So vision, image processing, speech recognition. So even though we're talking about deep learning, but deep learning really is a technology which just contains many parts, and all these parts are pieced together to provide a very good performance. So at the center of it is a deep neural network, and there are many different kinds of deep neural network. But essentially, all of them is trying to represent high-dimensional functions or high-dimensional probability in a fairly flexible and also powerful way. And besides that, we also have commonly used tools such as deep neural network itself, in a certain extent, is performing this automatic feature extraction. And there are other tools which play a significant role in deep learning, including things like optimization algorithms, like stochastic gradient, ADAM, back projection, which allows you to calculate the gradient effectively. And at the same time, all these nice software packages developed by various companies and also independent contributors. Most important thing is probably TensorFlow and PyTorch has played a significant role. And these allow us to leverage the computational power of GPU and TPU to achieve very good performance. Okay. Now, when we apply the deep learning to inverse problems, and we're faced with several challenges. The first main challenge is the limited amount of data. Okay. So when you're working with AI problems like speech recognition and image processing, classification, so on and so forth, you have a vast amount of data, for example, like ImageNet. Okay? But when you work with physics problems, coming like what we see in inverse problems, usually the amount of data is not so large, and for various reasons, some of them privacy reasons and also for financial reasons, these data are not always available to you. So therefore, the amount of data you can work with is actually pretty small. So the second challenge is that we're often in inverse problem setting, we're working with a regression problem rather than classification problems. So sometimes, I mean, we need not just a 0-1 answer, we actually need the actual number. So therefore, often we are required to have slightly higher accuracy. Okay. So the plan that I'm going to advocate in this talk is that we're going to use mathematics and physics of the inverse problems to design new neural network modules. These are tailored designed for inverse problems and also in general for problems with a certain mathematical structure. And I'll give two examples. One is pseudo-differential operators and the other is Fourier integral operators. Both of them play a significant role in the numerical computation of inverse problems. So once we have these new modules, and for a specific inverse problem, what we're going to do is that we're going to assemble the neural network using these modules, and at the same time taking consideration of various kind of invariance properties of the inverse problem itself. And the last step is that we're going to use the data to train the neural network from end to end. And once it's trained, you can deploy it and you can use it for inference and for solving the inverse problem. Okay. So the way we view it is that the main advantage of this approach is that it provides a seamless integration of the mathematical and physical structure of the problem, of the inverse problem, with the data that's given, the limited amount of data that's available for us. So here, the mathematics and physics, for example, is corresponding to the PDEs and also the very kind of statistical property of the inverse problem. And the data, you can view it, for example, in the medical imaging application, you can view it as the small amount of data which has already been labeled and provided by the doctors, for example. Okay. So, but by using this seamless integration, and in many cases, and we see that we can get away with a rather small data set. So the amount of data we need is not in the millions of the tens of millions, rather in some of the applications that I'll show you towards the end of the talk, and that we only need about 1,000 or 10,000 sample size. Okay. So, and the application I will go over in this talk is one from radar imaging, one from electron impedance tomography, and finally, there's another one come from travel time tomography. All right, so the rest of the part of this talk has two parts. So the first part is I'm going to talk about some new modules which related to inverse problems. And then the second one is, and then I'm going to go ahead and talk about some applications. All right, so the new modules. One, if you take a look at the popular neural network architectures, or here I like to use the word module because, well, I mean, you can assemble these modules together to make more complex networks. So if you take a look at the well-known neural network modules have been developed in the past 10, 15 years, or even longer, there are always some mathematical structure behind it. Well, this is not very deep observation, but it's just, but sometimes it's an important observation that we should keep in our mind. For example, if you take a look at fully connected neural network, well, I mean, it's essentially the linear version of that is just a dense linear operator you apply multiple times. And you add a nonlinearity to make it more powerful to represent nonlinear operators. And when we're working with image and vision applications, CNN is very powerful. but every layer of the CNN itself is implementing a translation invariant operator, which is essentially a convolution. And for residual network RNNN, in some sense, it's implementing a Markov chain. Because you're taking a state and you update it and you produce a state at the next time step and keep going. Finally, the resonant architecture, which has developed about, by now it's about 6 years ago, is essentially implementing, to a mathematical level, is implementing an ODE and time integration. Okay. So here, the pictures in the middle is trying to show you these architectures and its connection with these mathematical objects I talked about. So everyone, most of us, I mean, by the end of our high school, no, sorry, our undergrad education, so we have seen these objects. Okay, so when you start studying PDEs and you see a few more objects, so these objects here I'm listed below is the pseudo-differential operator and Fourier integral operators. So these operators are not as common as the objects I have just described, but they play a significant role in PDE analysis and also in inverse problems. So pseudo-differential operator, for example, models various kind of operators related to elliptic equations is extremely important in study elliptic and also parabolic equations. A Fourier integral operator, which is related to wave, is very important for hyperbolic equations. So the natural question we ask is that if we want to work with these operators, can we design neural network modules which are trying to represent these operators in an effective way? Okay, so let's just take a look at first the pseudo-differential operator. So, let's see, here I'm not writing down the exact definition, but if you have a pseudo-differential operator A, and by definition, you can view it in two ways. You can either view it in the kernel form, so it's going to be the integral of a kernel kxy multiply f, and you integrate over the y domain. So, and the y has to, the kernel k has to satisfy certain conditions. And or you can view it in the Fourier domain as almost like a Fourier transform, but with a certain multiplier, which denoted by ax c here. So as I said in the earlier slide, that it plays an important role in elliptic problems, Green's functions. And one very important thing about pseudo-differential operator is that when you apply to a certain function, where the location of the singularity of the output is aligned with the singularity of the input. And what this means is that when you view it, the whole pseudo-differential operator as a matrix, so the off-diagonal blocks, the blocks that are away from the diagonal, are typically numerically low rank. So this gives us a way to try to represent pseudo-differential operator in a very sparse and compact way. And so our plan is to try to use this sparse representation, compact representation, and try to use this to translate these compact representation into neural network, and then try to generalize to handle nonlinear cases. Okay. So, so the sparse approximation that we're going to use, and what I'm going to describe is something based on the wavelet transform. This is related to Stefan's talk, the previous talk. And the specific form that I'm going to use is something called a non-standard form of wavelet decomposition, and which I will describe in the next slide. So I would like to mention that besides the wavelet form that I'm going to talk about here, we can also use things related decomposition, such as fast multiple method, hierarchical matrices, and we also have some other work in that direction, but I'm not going to talk about it today. Okay, so what is this non-standard wavelet decomposition? So it's very well known in the wavelet community, but outside, in some sense, I think it deserves more recognition. So essentially, what this non-standard way of wavelet decomposition, essentially, instead of viewing this pseudo-differential operator as an operator, more like you're trying to which map from function to function, but rather you want to view it as a two-dimensional images. Okay, you want to view it as a bilinear form. Let's put it this way. So then, once you view it as an image, then you can try to use wavelet decomposition of the images, 2D wavelet decomposition, rather than just using 1D wavelet decomposition. So here, what I'm writing here is that try to represent this image in this building this wavelet 2D wavelet coefficients. And on the right-hand side, you have three matrices. The first matrices is actually doing this extended redundant version of the wavelet synthesis. On the right-hand side, you have the redundant version of the wavelet decomposition. in the middle, you can see that you have all these wavelet coefficients organized in this near diagonal pattern. The reason why it's near diagonal is because the singularity of the Fourier, pseudo-differential operators appear on the diagonal, while it's a smooth and away from the diagonal. So when you apply the wavelet, the coefficients will be close to 0. Okay, so the advantage of this approach is that it only keep a linear number of non-zero coefficients or close to non-zero, nearly non-zero coefficients. And when you apply this operator to a certain vector, it essentially involves only sparse multiplication, which is the middle matrix, and wavelet transforms. These are the two matrices on the two sides, on the right-hand side. Well, the good thing about this this non-standard form is that you can actually, when you apply this matrix in this non-standard form to a certain vector, it naturally decomposes into multiple scales. So at the bottom of this slide, I'm just trying to show you that what happens when you consider the application at a single wavelet scale. So this corresponds to on the right-hand side, I'm only taking the top left part. So as you can see that this multiplication on the finite scale, in fact, on any scale, but let's consider the finite scale. So the multiplication on the last scale can actually be represented as a convolution neural network with 3 layers. So the first you're going to do it's a convolution neural network where the input channel is a size 1 and the output channel is size 2, and the middle one is a two-channel to two-channel convolution neural network by multiplying these wavelet coefficients of the pseudo-differential operator, and finally you take from 2-channel back to 1-channel. Okay, so this is essentially every scale. It can be represented by a 3-layer neural network. So when you actually assemble all these things together, you cross all the scales, you get the following architecture. So in fact, that you can represent the whole multivec operation of this pseudo-differential operator to a vector. This hierarchical neural network where every layer itself is convolution, but you have the multiple layers. Okay, so in some sense, it looks like a harp. Okay, now. One can generalize this architecture by inserting ReLUs and by adding more convolution layers in the middle, and this will allow us to support nonlinearity, and this becomes quite powerful. So this net architectures we call it BCRNet because it's based on this wavelet decomposition scheme proposed by Belkin, Kaufman, and Rochlin almost about 30 years ago. All right, so now let's move to this Fourier integral operator, which is another important operator in PDEs and also in most problems. So the Fourier integral operator is another level generalization of a Fourier transform. Instead of having these multiplier A x c, you actually also change the phase function. So in the Fourier transform, the phase function is x dot c, but here is phi x c. Okay, now. So when you, it plays a big role in wave propagation and hyperbolic systems. And unlike the pseudo-differential operators where you keep the location of singularity, the Fourier integral operator actually moves the singularity around, but in a very well-defined way, governed by a Hamiltonian flow, which is related to this phase function phi. Okay, so this, in some sense, and also plus some smoothness condition, in fact, allows to represent the Fourier integral operator also in a fairly compact way. So from a numerical linear algebra point of view, is that when you view the Fourier integral operator in the matrix, and if you partition the matrix into square root of size blocks, so if you have n by n matrix, you partition into blocks of square root of n by square root of n. So you have many blocks. Each of the blocks is also reasonably large. Then all these blocks themselves are numerical low rank. So this has been proven, and this is a very important property of the Fourier integral operator. So based on this property, this allows to decompose the Fourier integral operator and also represent it in a very sparse way as a neural network, as you will see. And the specific tool that we use is something called a butterfly factorization, which has been developed by my students and I several years ago. So let me just show you what is the butterfly factorization. So if you give me an n by n Fourier integral operator size A, as I said, I'm going to partition it into, sorry, I should delete the word hierarchically. It's just one scale. So I partition it into the square root of n by square root of n blocks. So here I have a matrix of size 16 by 16 on the left-hand side. I partition to be 4 blocks. Each block is size maybe 4 by 4. Okay. Then, as I said, each of these small blocks itself is numerically low rank. So therefore, I can try to write it as a product of a one tall skinny matrix and also wide fat matrix. Okay. So each of the block. So with this I can approximate it by a tall skinny matrix times the fat matrix. Now the last step is that I'm going to reorganize this factorization of each of the block and write it into much more friendly linear algebra form. Is that I write it as a product of 3 matrices. So the first matrix is I organize all these tall skinny matrices. So there are 16 tall skinny matrices because I have 16 top blocks, but I'm going to organize in a block diagonal matrix where every 4 tall skinny matrix is combined into a 1 square matrix. So the last matrix on the second row is that I just assemble all the row matrices. And the middle matrix is very important. In fact, the middle matrix in some sense is that it really tells you that which row is linked to which, so which tall skinny matrix is linked with which fat matrix to give you the final result. Okay. So if you take a look more carefully, so what really this does is that, for example, if you take a look at the middle matrix in the second row, it map 1 entry. So all the all the white regions are 0. So you only have 16 non-zero entries. And what really this does is, in some sense, is it maps 1 entry to 1 to 1, map 1 to 5, and so on and so forth. So it's a little bit, hard to see. But now, if you index the rows and columns of this matrix, not with one single integer number, but with a pair ij, which varies from 1 to 4 for I and j. So therefore, and this is actually mapping from 1 entry to 1 entry, the top left corner. And then you'll see that all these non-zero locations of the middle matrix actually correspond to the flip of the 2 indices. So ij entry mapped to ji entry. Okay, so it's a switch of the indices. Now, why is this helpful? Well, the reason why this is helpful is that once we write the matrix in this form, applying this matrix to any vector self can be written very compactly into a neural network architecture. So when you apply the last matrix to the vector, the first essentially does is doing either convolution or local connected neural network. And so essentially you take a vector of 16, but you squeeze it into a vector of size 4 with 4 channels. Okay, so the number of degree of freedom still remain the same. And what the middle matrix does is that it switches the ij entry to the ji entry. So it's really doing the transpose of the middle matrix. So you have a dimensional 4 vector with 4 channels, and again you flip the essentially viewed as a small matrix of size 4 by 4, and then when you do flip it, it becomes another matrix of 4 by 4. Okay, but the channel becomes the spatial dimension, and the spatial dimension becomes channel. And finally, you have another neural network which take this 4 by 4, which is 16 two-dimensional grid, and just unfold it back to a vector of size 16. Okay. So as we did in the BCRNet, we can also insert ReLUs and add in a few more intermediate layers to make it more powerful, for example, to support nonlinearity. And this architecture, we call it SwitchNet, because really the most important step is the middle step where we do the transpose. Okay. Okay, so well, I talked about how to develop these effective representations for pseudo-differential operator and Fourier integral operators. So in the remaining of the talk, let's just put into some use. Okay, so the application I'm going to talk about is 3 inverse problems. So one is radar imaging, and the second one is electric impedance tomography, and the final one is travel time tomography. Okay. So the radar imaging is going to essentially use wave equations. Electric impedance tomography uses elliptic equations. And finally, the travel time tomography is also using wave equation, but using really the first arrival information of the wave equation. So you can think about like a high frequency asymptotic of the wave equation. Okay. So in each of these applications, I'll go through these applications one by one. And for each of the application, what I'm going to do is I'm going to design a neural network architecture for the inverse map of that specific problems. And then I'm going to train the neural network weights from end to end using the limited amount of data that I have. And finally, once you have the neural network ready, you can use it for prediction. Okay, so before I dive into the specific example, I would like to mention that in the recent years, there are many groups, many people been working on the deep learning for English problems, and with many different approaches. So here is just a list of the groups that I'm aware of, and there's also, I believe that there are many other groups are working on that. So I apologize for those I didn't put here, but certainly deep learning, many groups realize that deep learning can play a significant role in solving English problems. Okay, so the first example is radar imaging. This is joint work with my previous postdoc, Yu Hao Guo. And so here the setting is the following. So you have a domain omega where inside omega you have some unknown potentials, which are denoted by eta. Okay, sorry, I should, yeah, that's fine. So in fact, the equation is so the physics is governed by the so-called Helmholtz equation. So which is the Helmholtz equation is you have the certain the unknown is a field, which is we call the total field Ux, and the operator of the Helmholtz equation is very simple. It's minus Laplacian minus omega squared over c squared. So c is what we call the sound speed. And so in this picture, you can think about all the white region, the sound speed is equal to 1. So you can think about to be air or vacuum. But in this gray region, the Cx is not equal to 1. And this is something that we're trying to discover. Now, the omega here is called frequency. Okay. So the total field U typically can be decomposed into two parts. And one is this so-called incoming wave, Is, in a specific direction. So here, in the figure on the right-hand side, you have incoming wave in a specific S direction. So this is corresponding to the wave that you can you send it to this unknown domain. And then the second part is called US, is the scattered field. So when the wave hit this domain, if the domain is totally has nothing inside, C is equal to 1, then the wave is going to penetrate. But if you have certain perturbations, eta or here, then the wave is going to bounce back and forth and send to different direction, and this is the scattered wave. So to make a problem a little more easier to work with is that we can separate this C into two parts. So you can assume that there's a background velocity. So in the case of electromagnetic scattering or acoustic scattering in air, the C0 background velocity is just equal to 1 after certain normalization. So then recall that the unknown quantity is the sound speed in the domain Cx. So therefore, you can rewrite the Cx by introducing this quantity eta here. So the eta is defined to be omega squared over c squared minus omega squared over c0 squared. So instead of trying to figure out what the Cx is in the domain, it's equivalent to figure out what the eta is, right? Because they're just given by this very simple formula. Now, what is the data we recover? Well, the data we receive is that it's something called a far field pattern. So this is really, this is denoted by this US infinity R here. What this really is that you take the scattered field. So instead of looking at a finite location, you move yourself, your receiver, into infinity along a certain direction R. And then what you do is that you take your scattered field at this location moving to infinity, but rescaled it by the square root of rho and also rescaled by a phase function, okay, appropriately. So this quantity itself is, even though the scattered field itself is going to oscillate quite a bit, but this far field pattern itself is well defined, and it's going to a fixed constant as you move to infinity at a certain direction R. So this is my data. So this is I'm putting a lot of things here, but all you need to remember is that eta is an unknown quantity, and D is the far field pattern is what we receive, and the inverse problem is trying to figure out the eta based on D. Okay. Now now to work with inverse problem, so what we're going to do is that we're going to first look at the so-called forward problem. The forward problem is that suppose we know eta, and so how does the D depend on eta, right? So when we learn PDEs, we first study the forward problem always, right, to try to understand the physics. So let's make one assumption. Let's assume for the time being that eta is small, okay? And then in the case of eta small, we can use linearization. So after you do some maybe like 2-page calculations using Green's functions, you see that the data, which at the parameterized by R and S, where, let me remind you, S is incoming wave direction and R is outgoing wave direction. So the data at these two locations, in fact, can be written very compactly up to first order approximation at this integral of your eta, your unknown eta. Okay. Now, if you take a look at this kernel here, it's almost look like a Fourier transform, right? But it's because a Fourier transform exponential I omega something. So this almost look like a Fourier transform. And in fact, this is not quite a Fourier transform, but this is a Fourier integral operator. So this is the Fourier integral operator between two domains. So one domain is this two-dimensional unknown domain X, and the other domain is this product of the unit circle and the unit circle. So where this is where the space where my data is defined. So it's a Fourier transform. Sorry, it's a Fourier integral operator from the spatial domain X to this product of the two circles. These are the directional domains. Now, once it's a Fourier integral operator, we can try to see that whether this switch net idea works or not. So whether we can do this block decomposition. So in fact, we can. So here, the middle picture is trying to show you that we can partition my spatial domain omega into square root omega by square root omega blocks. And on the left-hand side, you can also partition your data domain S1 cross S1 into square root omega by square root omega blocks. And the interaction between any two blocks on the left, any block on the left and any block on the right is numerical low rank. So this allows us to use this SwitchNet module I talked about maybe 10 minutes ago, or maybe 5 minutes ago, to represent this operator A, this forward operator. And also, once you have this matrix, you can also do the transpose, you get its adjoint. And so the adjoint itself can also be represented by this SwitchNet. Okay. So, but we're not done yet because we only represented the forward problem so far. Okay. Now, how do we translate this forward problem to this inverse problem where you're given the data and trying to figure out the eta? Well, we're going to use another very basic tool in this problem. It's called a filter-back projection. So in some sense, it's just regularize the pseudo-inverse. Okay. So if you take the D, eta, we know that roughly at least in the small eta regime is, so D is given by A times eta. So therefore, if you do a regularized inverse, then eta can be more or less written as this inverse of the normal operator times this adjoint operator and times the D. Okay. Now, let's just motivated by this simple formula. Let's take a look at how we're gonna able to design a neural network architecture for the inverse problems. So the idea is rather simple. So you take your data D, and the first thing you're gonna do is you're gonna apply A star. So as we said, A star is adjoint operator, so therefore it can be represented by the SwitchNet. Okay, and then once you have that, you apply the inverse of the normal operator. And we can show that in this setting, the normal operator itself is pseudo-differential operator. And under reasonable assumptions, the inverse of the pseudo-differential operator is also pseudo-differential operator. So therefore, the second operator here can be represented by a BCR net because BCR net is designed to represent pseudo-differential operators. So therefore, you see that the whole architecture looks like the following, at least in this, if you decide to use this, the idea from filter-back projection is that you take your data D, you first apply the SwitchNet to mimic this A star operator, and then you apply this BCR net to mimic this inverse of the normal operator, and then that produces a result. So you see that here we're really using the physics of the problem to propose a neural network architecture for my inverse problems. But I haven't decided what kind of weight I'm going to put in this architecture because I haven't specified the coefficients. So these coefficients will actually be trained from end to end. So you're going to use limited amount of this small number of D and eta pair, and then try to train the problem, and hopefully that will give you an approximation of the operator which can be used for inference. So let me just give you one simple result. So here we're training with omega frequency equals to 60, and with the domain eta is discretized with this 80 by 80 samples. So omega is an 80 by 80 sample Cartesian grid. And the data domain RS, we sample them uniformly on this unit circles with about, again, 80 points per circle. Okay, so as I said, eta is the unknown, and so this is based on synthetic data. So we choose the eta to be a mixture of Gaussians. Here, I just show you in a simple example where you have 4 Gaussians. And we compute about 12,000 pairs of eta d pairs. So for every eta, we're going to do a numerical simulation to figure out what is the far field pattern, and that's my d. And I collect about the 12,000 pairs for training, and also reserve another 12,000 pairs for testing. Okay. So, and the picture here is trying to show you that what kind of error we get for the inverse map, which approximates the neural network, and also what kind of error we get the forward map. So you see that the neural network results and also the ground truths are almost indistinguishable visually. So, and if in fact you take a look at the error, the inverse problem have about 1% of error, and the forward problem about 4% of error. So it's not well, the error is still noticeable, but on the other hand, I think it's sufficiently small that it becomes useful for inverse problems for scattering. Okay, so the second example is electric impedance tomography. So here the physics is slightly different. It's really an elliptic equation. So the operator is minus Laplacian minus the eta, where eta is unknown potential. Okay, so the x corresponds to the horizontal axis and z corresponds to the vertical axis, which we typically call depth. So what is the so eta is unknown. So what is the data that we check here? Well, the data is actually something which is called a Dirichlet-Neumann map. So what you do is the following: is that for every boundary point, so the top surface is a boundary point. For every boundary point, you can put a delta source over there, and then what you do is that you solve this PDE in the domain, and you measure the normal derivative. Here, the arrow stands for the outward normal derivative at all the top surface. You measure the normal derivative and you record them. Okay, so that will give you a function which depends on the receiver location. Now, if you iterate over all the possible source directions, and that again give you a function with two variables, and that is something called a Dirichlet-Neumann map, and that's my D. So the problem that I'm trying to solve is that the inverse problem is that suppose I have a discretization of the Dirichlet-Neumann map. How can I discover the interior property? Well, the way to do that is the following: is that well, we're going to consider again also the forward problems. So after again making some small eta assumptions and by doing some PDE calculations, and you can see that this output, the Dirichlet-Neumann map itself, can in fact be written as a kernel, where the kernel is given by the product of the free space Green's functions at the two locations. And this linearized operator A here, in fact, has a very nice hidden convolution structure. So in fact, you can't directly see it here, but after dual coordinate transformation become very clear. So instead of reading the data at the receiver source locations, but instead you transform the coordinate into a midpoint and also the offset. So I'm denoted here by M and H. So M is essentially the average of R and S, and H tells you.
Lexing, you have just a couple minutes more. Sorry.
Okay, sure. Yeah. Okay, I'll speed up. So then, what you do here is that you rewrite this this operator in this new M and H coordinate. M is middle point, H is offset. And then once you do that, you clearly see that the convolution structure between M and X pop up. Now the H coordinate and also the coordinate are really serving as the parameters. And the more importantly is that, and also equally important is that the Z and H coordinate are really highly compressible. Okay, so this suggests the following neural network architecture. And the following is that we essentially, you're going to use, again, we also follow this filter back projection mechanism. So what we do here is that we're going to use the neural network to approximate A star. But as we said, that A star itself is a hidden 1D convolution structure. So therefore, it can just simply used by 1D CNN. So we don't even need to use fancy things like SwitchNet. Okay. And then the inverse of the normal operator is represented by the pseudo-differential operator, which is again by BCR. Okay, so again, the whole thing is trained end to end, and using the data that's given to us. So let me just go to this example very quickly. So here we are trained with about 80,000 pairs of eta, the eta and the D pairs. So again, numerical simulations used to compute this Dirichlet-Neumann map. And we also reserve 8,000 pairs for testing. So in this case, the inverse map gives you about 8% of the error. And the reason here is the following, because this problem itself become elliptic, based on elliptic operator. And so therefore the inverse problem is actually very ill posed. And 8% error is actually a pretty good performance in this setting. Okay, so let me just go quickly using 2 minutes to explain what is the last application, is the travel time tomography. So the travel time tomography, the PDE is given by this so-called Icona equation. Okay, So, so assume that the media is mostly 1 inside the domain, but there's certain perturbation m tilde, which moves certain regions to have sound speed greater than, slowness greater than 1, and some locations will have slowness less than 1. So, and this m eta is unknown quantity that we're trying to discover. So what is the data, the boundary data here? The boundary data is the solution of this so-called iconic equation. So what we do is that at the source location, you specify source location, which is called xs, and then you set the solution of the iconic equation to be 0 at the source. And then you solve for the iconic equation everywhere else. And then what you do is that for every receiver point, which is denoted by xr, you record the solution of this iconic equation with the source, with the solution equal to 0 at the source. Okay, so this is called the travel time. Now the travel time is not going to be a very simple function because the media is quite complicated. You have this due to this m tilde. Okay, and again, this data that you receive is a function of 2 variables, and this is d is the travel time from the source to the receiver. And the inverse problem itself is the same, is that you're going to try to figure out from the travel time what is the media perturbation. Now I'm trying to so the idea here is very similar. So you use a linearization to figure out what's a forward map, and the main point here is that here the problem itself has a rotation symmetry. So by using this rotation symmetry, so we can write the data not in the receiver source domain, but the source and also offset domain edge. By doing that, you also recover a hidden 1D convolutional structure. And by using this hidden 1D convolutional structure, you can represent these forward operator A and also A star using the convolutional neural network. And by following the same process, we can write the inverse problems by using filter projection. And this also motivates the same architecture by using 1D CNN to mimic A star and also use a PCR to mimic this inverse of the normal equation. Sorry, due to the, sorry, I'm running out of time, but let me just show you one picture. So this is what we obtained numerically. So we use 20,000 pairs for training and also 20,000 pairs for testing. What I'm trying to show you here is that our algorithm, our neural network architecture is very robust against noise. So here I'm showing you every row stands for different set of occlusions. Some are positive, some are negative, some are mixed. And different columns correspond to different noise we added to the data. So you can see that even we add 10% of the noise, we can able to recover the shape and also location of the inclusions very accurately. Okay, to summarize, so in this talk has 2 parts. The first part, I talk about some new neural network modules to approximate to represent pseudo-differential operators and Fourier integral operators. So I also talk about a few applications. Okay, the main takeaway message, if you just want to remember one thing, is that so in those problems, it's useful to use mathematical physics to try to motivate the architecture of the neural network, while you're going to use a limited amount of data to decide the weights. Okay, so with that, I'd like to thank you for your attention, and I'm ready to take questions.
Thank you very much for the beautiful talk, Lexing. We have about 5 minutes for questions. The first question we have is there a connection with this neural network structure based on wavelet transform in the scattering net that was mentioned in the previous talk? And it looks like after you answer this question, Stefan Malat is also willing to have a discussion.
Well, they both use wavelet, but I guess it's a slightly different because in the scattering transform, you calculate all the wavelet coefficients and you add the ReLU, and then you do another level of wavelet coefficients multiple times. But here, essentially, wavelet is only used once. Maybe Stefan want to add a few comments.
Stefan, are you?
Yeah, I think you're right. It's really quite different. You're using the wavelet here as a wavelet basis in order to compress the underlying operator, whereas in the scattering transform, it's used for scale separation to build different type of invariants that are going to compress the underlying process. So it's different, yet it's probably not by chance that both comes in within these structures. So I mean, scale separation is behind, but technically I fully agree with what you said. It's really different.
And I also want to add one thing is that in this case, the wavelet coefficients, the wavelet filter is actually trained. But I guess in Stefan's talk, I mean, you can, for example, as he mentioned, you can use a one fixed wavelet and that still work quite well. So in our case, we actually train the wavelet coefficients, the wavelet filters.
Thank you. Lexing, are you done with your screen share?
Yes, okay, I can stop sharing, yes.
Okay, but we still have time for another question.
Sure.
For you. We have the question, would it be possible to generalize your work to solve these inverse problems in the nonlinear regime?
Well, I mean, these inverse problems themselves, I would say they're already nonlinear, right? Because, well, I mean, they're given by linear PDE in most of the cases. For example, in the EIT case, electroimpedance tomography, or the scattering case, they're given by linear PDE, but the inverse problem itself is highly nonlinear. Okay, so in fact, the last application I talk about, which is this travel time tomography, that itself is a nonlinear PDE. So in some sense, we're already touching the nonlinear PDEs, but I guess there are a lot of other nonlinear PDEs out there. So, well, I mean, we're ready to look at them more closely. So I want to add one thing. The linearization is used only to motivate the design of architecture, but the architecture itself is actually, the implementation of the inverse map itself is actually highly nonlinear.
So by encoding via Fourier transform, are there implicit regularity requirements for the inclusions? It seems in the final example that you were able to recover sharp representations of piecewise constant inclusions.
Okay, so there's two. Can you hear me? Hello? Yeah. Okay. So I think there's. Okay. Let me answer the first question first. So do I add the regularization of my approach mostly come from the simplicity of the model. So one thing I didn't emphasize is that in our case, the model is rather simple. And for example, in many cases, it's a BCR net and a 1D Fourier, 1D convolution neural network. So therefore, the degree of freedom, the number of weights in the neural network are much smaller than, in fact, the data size, even though, I mean, data set size is also pretty small. So therefore, the regularization really comes from the simplicity of the structure. And so we're not in this over-parameterization regime and try to use implicit regularization. So in some sense, the simplicity of the structure give explicit regularization. And the second part of the question is related to the sharp feature. So, well, I guess, I mean, the way to explain that the construction has sharp feature is because that the neural network, the data itself has sharp features. So, which the training data itself has examples where you have the sharp boundaries. And so naturally, the neural network, when you actually trying to during the training phase of the neural network, you want to produce the results which have similar features. So in some sense, I think the nice thing about the approach is that the approach itself respects the physics, but at the same time is also implicitly learning the prior on the data. So if you train with data with, for example, solely with sharp features, it will recover sharp features better than the smooth things, I believe. And if you train data mostly with smooth samples, then I guess during the recovery, you will see smooth reconstruction more likely than sharp features. I hope this answers your question.